Okay. So, over here, you got to see the setup. Okay, so here's the setup. I have two strings, okay, over a set of pulleys that allow this to move, okay? So I have a 1/2 kilogram mass on one side. I have an identical 1/2 gram mass on the other side. And I have a scale in between that reads the amount of force that's on the system, okay? So right now, obviously everything's in equilibrium. Nothing's accelerating. So there's three options in terms of the reading that's on the scale. It's multiple choice. So the system's here. I got a 1/2 kilogram mass, 1/2 kilogram mass. I got the spring in the spring scale in between. Option A, the reading on the scale is 0 because nothing is accelerating and it's being pulled equally in both directions. Okay, so option A, when I lift this up, the reading on the scale is 0 newtons. Okay. Option B, the reading on the scale is 9.8 newtons because I got a 1/2 kilogram mass pulling on one side, I got a 1/2 kilogram mass pulling on the other. The combined, each of those is 4.9. Reading on the scale would be 9.8. Okay, so option A is 0, option B is 9.8. Option C is 4.9 newtons because it's effectively only being pulled on one side. Okay? And a 1/2 kilogram mass weighs 4.9 newtons. Okay? So those are your three options. It's 0, it's 9.8, or it's 4.9. So how many are on the 0 train? 1?
Yeah.
Vitor?
Nah.
You wanted to.
I was,
You thought about it.
nah,
Okay?
I don't think.
What about the 9.8 train? 1, 2, 3, 6. Okay, the vast majority are on the 9.8 train. Louis, why are you on the 9.8 train?
Because if there's 4.9 newtons acting this way, 4.9 newtons acting that way, then the scale is caught in the middle. It's only measuring from one side, not both. So it's got an effective, I guess, reading of 9.8 from one side because it's getting pulled in that direction and that direction.
Okay? So it's being pulled in both directions, so it would be in effect pulling the sum total of both of those, which would be 9.8.
Gotcha.
Keaton, what are you on? Which train are you on?
I was thinking 4.9 at first because the spring scale should be measuring the force applied, which I guess it could change depending on which way you view it, as one force being pulling it this way being the force applied, the other being the opposing preventing it from moving that way.
Okay?
And if there's 4.9 newtons pulling it this way being the applied force, the opposing force is also 4.9, but I thought spring scales only measured the applied force, so it'd only be measuring half of it, which would be the 4.9 acting on one side.
Okay? Huh. Before you answer the question, let's see if any of you might want to re-vote, okay? What if I just held this end of the spring and there was nothing over there? So in other words, I'm going to take the weight off of this side, okay? I want to lift up on this, and I'm just going to hold this.
Yeah.
What's the reading on the scale? 4.9 newtons. So if this was tied to a wall, you'd be reading 4.9 newtons. Everybody cool with that?
Yeah.
Okay? So now, that's in effect acting as a wall. So the reading on the scale is 4.9 newtons. Okay? Because basically what's happening is that this is just acting as an anchor. It's just holding it there. Now, the system isn't accelerating, right? Now, what if I gave a problem like this? Which is a very real possibility on the test tomorrow. Let's say that I put a 1 kilogram mass over there, and let's say I put a 1/2 kilogram mass over here. And let's say that I take a hot plate and I put it in between where this whole thing would drag like this. Okay? So, at the end of the day, so I let go of this system, and imagine this thing is accelerating in this direction. So what do you know about this applied force here relative to the opposing forces in the opposite direction? It's got to be greater than. Okay? If there's friction and this thing is going in this direction, which direction is the frictional force going to act? Opposite direction. So when you calculate a frictional force in a situation like this, only use the weight of this, okay? The weights on the end are just applying the forces. So when you have to calculate a frictional force, only use the weight that's on that table that's being moved. But when you calculate the acceleration of the entire thing, and you're going to use force net equals mass times acceleration, which mass do you use? The mass on the end, the mass on that end, the mass of the hot plate, or the combined mass of the entire system? Always divide by the combined mass of the entire system, okay? This just contributes to the frictional force, okay? But at the end of the day, when you're going to calculate that acceleration, you divide by the combined mass of everything. Okay, now, give that a turn. We're going to go over here. Now, while we're here, let's just go here. Okay, so I promise you there's going to be like a elevator problem, or which is a combination of an elevator or a helicopter. Okay, so here's this helicopter, okay? And let's say that it has a mass of, I don't know, 1,000 kilograms, and let's say that the upward force from the rotors is, I don't know, 50,000 newtons. And I want you to calculate the acceleration of the helicopter. What are you going to do?
Find the normal force. Or find the
No, find the gravitational force.
I got to find my gravity. You always have to pay off the friction, off the gravity mafia, right? So what does a 1,000 kilogram helicopter weigh on Earth?
9,800 newtons.
Yeah, multiply that by 9.8, you're going to get 9,800 newtons. So when in doubt, set up a chart. Force applied, force opposing, force net. So in this case, I've got a 50,000 Newton force acting up. I got a negative 9,800 Newton force acting down. That leaves me a net force of 40,200 newtons, which is way out, this is huge, okay? Realistically, we don't be this big. But then you're going to take that, divide that by the mass to get your acceleration. The same thing would be true if you're in an elevator, okay? So if you're in an elevator standing on the scale, okay, if that accelerates upward, what's going to happen to the reading on the scale? It will be above or below what you weigh?
Above.
Above. So if you accelerate upward, that force applied will be greater than your Fg. If you're accelerating downward, that force applied will be less than your gravitational force. Okay? Promise you there's going to be questions like this. Okay? Make sure that you understand those. All right, now let's go back over here, kind of where Pop is. So just give that a spin. So what we have here is, this is a very, very strong magnetic place. Here, that's what you do, like one side, or Hilton Spring camera. Okay, so this is one strong magnetic base, and this is also a very, very strong magnet. So what I'm going to do is I'm going to give this a spin, which is the hardest part. Take that.
Whoa.
I just had it going. Okay. Now give that a lift.
No way.
Okay? So, when it was hovering, what do you know about the forces?
Equal.
They're equal and opposite, right? So this situation where you can have forces acting, but you don't have an acceleration. So the reason that's so critical, and this is why it looks kind of janky, but this has to be a very, very small tolerance, because basically what's happening, and it only works if you try and do that and it's not spinning, it won't work. So it has to spin so that it stabilizes, because it has an angular momentum vector. So if I give that a spin and get it going, This is the hardest part. Whoa. There we go. That's a good one. So as that stabilizes, you reach just one point. As I say that, where that's going to hover. Okay, the name of time. Now, we got to move over here to this. So,
I do too.
Say hi to level
okay. So I promise you, there's going to be a question going to be on your test like this. Mainly because it combines a whole bunch of different things. So I've got the magnet, I've got an inclined plane, and I've got, so I'm going to let go of it, okay? So obviously, what's the direction of the net force? Downward. So when I let go of this thing, first off, let's start with the magnet. Does the magnet ever make it speed up? No. This is what you all should see out of your lab. The magnet only acts as a braking force, okay? So, and on this problem, I'm going to tell you exactly how I want the system defined, okay? So I'm going to define downhill as being a negative value. So when I let go of it, obviously, what's the direction of the imbalance force? Downhill. So what's the force that's making it go downhill? Force parallel. How do you calculate force parallel? FG, sine theta. So I've got a force parallel that's acting down. What's the force from the magnet? Force from the magnet's always an opposing force, right? So if this thing is going downhill, what's the force from the direction of the magnet?
Uphill.
It's acting uphill, right? So I've got the force from the magnet going uphill. I've got the force parallel going down. Now, at the end of this, I got a 20 gram mass. So, which direction is that force, when I let go of this, which direction is that force acting?
Uphill.
Uphill. Because that's trying to produce, because this thing is trying to drag this thing uphill. So, I have three forces. I have the force parallel going down. I have the force from the magnet acting up. I have the force from the weight acting up. Obviously, which of those three is the biggest? Force parallel. So when you would calculate that net force, you would sit here and go, okay, I got this force going down, which has to be bigger than the weight going up and the force from the magnet going up. I will give you the numeric value of the force from the magnet. You just have to know how to use it. So what you got to be able to do on this problem tomorrow, you got to be able to calculate the force parallel. You got to be able to find the force from the end of this string. Use all of that to find your net force. Then you're going to find the acceleration. How are you going to find the acceleration? Take your net force and divide it by the total mass, including
The
car
car
and
and
the
Mass at the end.
and the mass at the end, okay? Don't forget that step. Okay, what I'm going to do is I'm going to give you a review, okay? If you want to do it, great. I'm also going to give you the answer key to that review. So, I'm done. As you contemplate things, remember Newton's 3 laws of motion.
Smart.
Law of inertia, F equals ma. For every action, there is a
Equal amount of
reaction. Think of an elevator. When do you feel heaviest? When do you feel lightest? When would you feel at a constant velocity? Okay, I'm done. I'll hand out those reviews. Here we go.